Hey guys, today we're getting into something really exciting. We are going to talk complex numbers. So complex numbers are numbers that are not real, or a combination of real and non-real numbers. So far, everything in Algebra 1 and Geometry has consisted of real numbers, but we're going to start talking about imaginary numbers. So in the past, you've been told x squared equals -1. That's not solvable with information that we know. But now, we're going to be able to say that if we take the square root of both sides, we get x is equal to, plus or minus, always when we take the square root, one imaginary number. So let's talk about what these imaginary numbers really are. It's important that you know that I is equal to the square root of -1. So then I squared is the square root of -1 times the square root of -1, which then just is -1. So I squared is -1. I to the third happens to be the square root of -1 times the square root of -1 times the square root of -1. Well, we know that these first two would equal -1 times the square root of -1, which we said is I. So this is -I. So I to the third is -I. I to the fourth, then, is the square root of -1 times the square root of -1 times the square root of -1 times the square root of -1. Well, these two would be -1. These two would be -1. -1 times -1 is +1. This says the pattern repeats. Here's what's important to know. If I went to I to the fifth, that's the same thing as I to the fourth times I to the first, right? So then I to the fourth we said is just 1, and then we have I. I to the sixth is I to the fourth times I to the second. So that's 1 times I squared, or times -1, which would be -1. So look, we've gone from 1I to -1. You can try it with I to the seventh, is I to the fourth and I to the third. So then there's our I to the third left over. That gives us -I. I to the eighth is I to the fourth and I to the fourth. So that's 1 and 1 again. So simplifying complex expressions. We always simplify any I that has a power greater than 1. So I to the 20th, what we're looking for here, notice what I did each time here, was take out as many I to the fourths as I could. And then I noted what was left over. So with I to the 20, it's really just I to the fourth times 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 I to the fourth. And we know that all of those, or I to the fourth to the fifth power, I to the fourth is just 1. So we have 1 to the fifth power, or just 1 here. I to the 18th, we have I to the fourth in there 4 times. That gets up to I to the 16, and then we have I squared left over. What was I squared? I squared was -1. So we have 1 times -1, or just -1. I to the 33rd. Well, I to the fourth 8 times gets us to I to the 32nd, and then we have 1 I left over. So our answer here is just I. I to the 41st, we have I to the fourth 10 times, and then we have 1 I left over. So just I is our answer there. All right, try some different numbers, see how you do with that and simplifying. All right, so then if we know that the square root of -1 is I, then the square root of any negative number, r, is the same as the square root of -1 times the square root of that r value. So then we know that we have I in the square root of that real number. So the square root of -16 is the same as saying the square root of -1 times the square root of 16. So then we have I times 4. But typically we write the coefficient first. We write that number first. So 4I is our answer. The square root of -48, we can take out the square root of -1. And then I'm going to go ahead and pull out a perfect square of 16. And then I have a square root of 3 left over. So, like I said before, we're going to put that number out in front first, then I, and then we have radical 3 left over. So 4I radical 3. All right. We have I to the square root of r squared. So that is I squared. And then we have radical r squared. What that tells us is I squared is -1. Square root of r squared is just r. So we get -1r. When we're talking about this complex number, so that was the title of our lesson today, was complex numbers. The A is the real part, and the B is the imaginary part. So when we add and subtract, we collect like terms. We treat that I kind of like it's a variable. So when I add and subtract here, I just do 3 plus 4 is 7. And then I do 2I plus -6I, and I get a -4I. Same thing when you're subtracting, so 2 minus 5 is a -3. And then -3I minus 2I is -5I. When we multiply, we do the same kind of thing. So when we use FOIL, we have 8 times 3 is 24. Outside is plus 8I. Inside is -6I. And last is -2I to the second power. So now that's where things are a little bit different, because then I have 24 plus 2I, and then I have -2, and then I squared we know is -1. So now I have 24 plus 2I plus 2. So I can rewrite that then as 26 plus 2I. With this one, we're just distributing. So 3I times 2 is 6I. And then 3I times 4I is 12I squared. But we know that I squared, again, is -1. So we have 12 times -1. So I end up with -12 plus 6I if I write it in the A plus BI form. Okay, so when we divide, we multiply by the complex conjugate of the denominator. The complex conjugate is just the opposite sign in front of the imaginary number. So if you have A plus BI to start, A minus BI is the complex conjugate. If you have A minus BI, then A plus BI is the complex conjugate. So in this case, we have 1 plus I. We are going to multiply by 1 minus I in both the numerator and the denominator. And then we're going to multiply straight across the numerator, and we'll multiply straight across the denominator, and that will get rid of the imaginary number in the denominator. So when I multiply across the top, I'm going to FOIL. So 2 times 1 is 2. Outside, I get minus 2i. Inside, I get minus 7i. And last, I get plus 7i squared. Over 1 times 1. Outside is minus 1i. Inside is plus 1i. And last is minus I squared. Okay, so now I'm going to simplify this. I have 2 minus 9i plus 7 times negative 1 over minus 1i plus 1i cancels. So I have 1 minus, and then I squared is negative 1. So 1 minus a negative 1 is going to give me 2 in the denominator. Then I have 2 minus 9i plus 7 times negative 1 is going to give me a negative 7. So 2 minus 7 is negative 5 minus 9i. There's my answer. That is the simplified form there when we're dividing. Now, in this one, I only have a minus 2i, so I have 0 reals. So if I have 0 minus 2i, then I'm going to multiply by 0 plus 2i, or just 2i. So then it's more like I'm distributing here in the numerator. So 2i times 3 is 6i, and then 4i times 2i is 8i squared, and I have a plus sign in between those. I have negative 2i times 2i is negative 4i squared. So 8i squared then is 8 times negative 1, so that's a negative 8 plus 6i over negative 4i squared is negative 1, so negative 4 times negative 1 is 4. But now, I can simplify that because all of those are divisible by 2. So I get negative 4 plus 3i over 2 is my final answer. Okay, taking the absolute value of a complex number. If z is equal to a plus bi, then the absolute value is equal to a squared plus b squared. So we're ignoring the I piece of this when we are taking the absolute value. We're just saying the square root of negative 2 squared plus 5 squared. So we get 4 plus 25. So the absolute value is the square root of 29. We'll talk more about this one in class and why this works and how it works. So we will see this one again. All right. Now, let's talk about solving, since that's what we've been doing the past chapter or the past lessons. Let's go ahead and solve this. So I'm going to probably try to solve by square roots since there is no middle x term. So I'm going to move this 26 over. And I get 2x squared is equal to negative 36. I'm going to divide by 2. And I get x squared is equal to negative 18. Okay, so this is what we talked about on the first page, that then in the past we've said, oh, well, there's no solution. If there's no real solution, we can find the imaginary solutions, though, now. So I get x equals plus or minus, and I'm going to go ahead and say negative 1. And then my largest perfect square would be 9, and then I have 2 left over. So I get x equals plus or minus. Square root of 9 is 3. Square root of negative 1 is I. And then I have radical 2 left over. If you want to take a second to pause the video, you'll notice this 2x squared plus 36 is your graph. Go ahead and pause and try to graph that on the graphing calculator. What you should have noticed is when you went to graph this, it didn't touch the x-axis anywhere. It probably looked something like this. I have no scale there to see where it fell, but it looked something like that. All right, this one as well, same kind of thing. If we're solving this, again, you could multiply that whole mess out like we talked about in previous lessons, but I'm going to just try to use square roots to solve. So I'm going to multiply both sides by negative 2 to cancel out that negative 1/2. Then I just have x plus 1 quantity squared is equal to negative 10. Now I'm going to take the square root of both sides. So I get x plus 1 is equal to plus or minus. I can take out an I, but nothing else is going to come out of there. So then I'm going to subtract 1 from both sides, and I get x equals negative 1 plus or minus I radical 10. Again, go ahead and pause the video and try to graph that. You'll want to move that 5 over so you get negative 1/2 x plus 1 quantity squared minus 5 when you solve that, or when you moved it over. So in vertex form there for you. All right, last piece then, and I told you we would come back to this in a previous lesson, factoring the sum of squares. We said we could only do the difference of squares. Well, turns out the sum of squares does work, but not with real solutions. So rewrite a sum of squares as a product of a complex number and its conjugate. In other words, factor the binomial. So x squared plus 4 happens to be x plus 2i and x minus 2i. 36x squared plus 121 happens to be 6x plus 11i and 6x minus 11i. All right, guys, that is it for today. So if you have questions, please come in and see me. Otherwise, I'll see you in class.